We've already looked at how to solve polynomial inequalities, and so now we're going to expand that reach into rational inequalities. We're going to use many of the same processes, but we must first assume that all of these rational functions are in reduced form. A rational inequality is just a rational expression, a rational equation where we've replaced that equal sign with a less than, a greater than, a less than or equal to, something like that. And just like with polynomial inequalities, if we can graph and determine the intervals on which the function is positive or negative, we can solve the inequality. Recognize that graphing rational functions can be more difficult, so we need an algebraic method to solve these. When we had polynomials, as long as there were continuous intervals, we could rely on the sign change method. And we note that rational functions are not always continuous, but we know very specific places that they aren't continuous, the asymptotes, the holes in the graph, things like that. So if we pay attention to these asymptotes, then we can still use this method. Take a second to pause the video or go to OneNote and copy down these steps, and then we're going to work through them on several examples. For example 1, let's look at the inequality, rational inequality, x squared plus 1 over x squared plus 2x minus 15 is greater than 0. We notice if we're following our steps here, we want to find the real zeros of the numerator. There are no real zeros. We want to find the real zeros of the denominator, which are going to be our vertical asymptotes. We've done this in a previous problem. When we factor this, we're going to get that our vertical asymptotes are x equals 3 and x equals -5. Those are the places that we need to pay attention to. We're going to place these values now on a number line. And then we're going to check each interval. I'm going to choose for this area here to the left, I'm going to choose -8. And when I plug in -8, I get 64 plus 1 over 64 minus 16 minus 15, which all I care about is that it ends up positive, which makes the statement true. So this is in my interval. For my middle area here between the two dots, I'm going to choose 0, which leaves me with 1 up top and -15 on the bottom, which is not true for this statement. So it is not one of the solutions. And for my third section, I'm going to choose the value of 10, which leaves me with 101 over 100 minus 20 minus 15, which is positive. And this results in, we know the interval solution here is going to go from -infinity up to -5 in union with 3 to infinity. And note we're using parentheses there. When you're solving these algebraically, it is vitally important to write inequalities in standard form. And by that we've got to get them equal to 0. If not, you may end up inadvertently multiplying by or dividing by a negative. So for example, if you had something like this and you multiply to bring this up, you're assuming there that x plus 2 is a positive number. Because remember, if it's negative, we would have to flip this inequality. But notice if you solve that, if I plug in something like -2.5, which if you solve this ends up in the solution, then I end up with -2.5 plus 2, which results in a +5, which according to this should be less than 3. And 5 is not less than 3. We assumed x plus 2 was positive, but we didn't consider the negative. So let's look at how to take this into account. We're going to solve two inequalities simultaneously. So let's look at x over x plus 2 is less than 3, and x over x plus 2 is less than or equal to 3. Again, get it in standard form. So I'm going to subtract 3 from both sides. I get x over x plus 2 minus 3 is less than 0. And I get x over x plus 2 minus 3 is less than or equal to 0. Remembering our steps where we have to find a common denominator, this becomes x minus 3 times x plus 2. We assume this is over 1 over x plus 2 is less than 0. And here we get x minus 3 times x plus 2 over x plus 2 is less than or equal to 0. As we continue our process here of combining like terms, we get x minus 3x, which ends us with negative 2x minus 6 over x plus 2 is less than 0. Likewise, negative 2x minus 6 over x plus 2 is less than or equal to 0. When I factor the top now, I'm following the steps now that I have it in simplest standard form. If I pull out a negative 2 here, now I can divide this by negative 2, which tells me to flip this inequality. So I end up with x plus 3 over x plus 2 is greater than 0, or x plus 3 over x plus 2 is greater than or equal to 0. Following those steps, we need to find the zeros of both the numerator and the denominator. We see that one of those zeros is negative 3, and one of those zeros is negative 2. This value can never be included even when there's an equal sign, because notice negative 2 is not in the denominator now, or in the domain. Now I'm going to follow the same process. I'm going to pick a point over here. I'm going to choose negative 5. When I plug in negative 5, I get negative 5 over, sorry, I left off my values here, negative 5 plus 3, going back to this equation, over negative 5 plus 2. And notice that comes out to be a positive number, a negative divided by a negative, which makes this statement true. This is included in the interval. When I plug in the value of, say, negative 2.5, I'm picking something in between. I have negative 2.5 plus 3 over negative 2.5 plus 2. That comes out with a positive divided by a negative, which leaves me with a negative number. These are not included in the solution. And last but not least, if I choose x is 0, I end up with 3 over 2, which is indeed positive, which makes this true. So for our first inequality where the equal to is not included, our solution goes from negative infinity to 3 in union with negative 2 to infinity. But for our second interval, notice we go from negative infinity, this should be a negative 3, to negative 3 with negative 3 included in union with negative 2 to infinity. This is what I was talking about before. That stays a parenthesis because if you include negative 2, that denominator is going to become 0, which we know is undefined.